Welcome to our Precalculus class for STEM students. Today's lesson is sigma notation. To start, let us describe and define what a sigma notation is. Say for example your teacher asks you to find the sum of the first 6 terms of the sequence, 2, 3, 5, and so on. You might think that the sum of every succeeding terms increases by 1 each time. Hence, you might have 2 plus 3 plus 5 plus 8 plus 12 plus 17. Unfortunately, your teacher might be thinking 2 plus 3 plus 5 plus 7 plus 11 plus 13, or the sum of prime numbers. This is where summation, or sigma notation, becomes advantageous. Summation, or sigma notation, is a method used to write out a long sum, in a concise way. It uses the uppercase Greek letter sigma, as its symbol, or operator. Say for example, your teacher asked you to add all the numbers from 1 to 100, we can write the given this way. Which is way too long that it would take up so much time, and space, to write. Whereas if we write it in sigma notation, we can just write it this way, which is read as, the summation of I, as I, goes from 1 to 100. This is an example of sigma notation. Now, let us try to inspect its parts. First, we have the summation symbol, which is, again, the uppercase Greek letter, sigma. I, placed on the lower portion of the summation symbol, refers to the index of summation. It sets the lower limit of the summation, or the number used to generate the first term in the series. The stopping point, or the upper limit, is the number above the sigma, that is used to generate the last term in a series. Lastly, the typical element or the summation term, of the sequence which is being summed, appears to the right of the summation sign. Again, this sigma notation is read as, the summation of I, as I, goes from 1 to 100, which tells us to add all numbers from 1 to 100. This, for example, is read as, the summation of 4I, as I, goes from 1 to 100. To deal with this, we are to substitute our I, in the summation term or the typical element, with numbers from 1 to 100. Hence, our first term of the series would be 4 times 1, which is 4. Our second term would be 4 times 2, which is 8. Our third term would be 4 times 3, which is 12. All the way to our last term of the series, which is 4 times 100, which is 400. Next, this is read as, the summation of 2I plus 3, as I, goes from 0 to 50. The series when we substitute I, with 0 to 50, would be 3 plus 5 plus 7 plus 9, and so on, plus 101 plus 103, which is the last term. In this last example, this is read as, the summation of 2I squared, plus 1, all over 2, as I, goes from 0 to 50. We can, again, substitute 0 to 50, to I, so that our first term would be 1/2, all the way to our last term, which is 2 times 50 squared as 5,000, plus 1 is 5,001 over 2. Previously, we learned that, by substituting I, with the lower limit of the index of summation up to the upper limit, we can expand the sigma notation into sum of numbers or series. Now what if your teacher asked you to express the sum of these numbers into sigma notation? The first step would be finding a rule that can represent this series, with this being the first term, the second term, the third term, and so on, up to the last term. By simple observation, we can establish that this series is the sum of even numbers, R2x, with x as the numbers from 1 to 100. Hence, we can write this in sigma notation as, the summation of 2I, as I, goes from 1 to 100. Now what if we have oscillating signs, or signs that are alternating in the series? So, how do we establish the rule for this? Try to observe this to gain an insight. If we are to raise -1 by 1, 2, 3, 4, and so on, then we have the sequence -1, 1, -1, 1, and so on, or the sequence with alternating signs. It can be represented by the rule (-1 raised to n), where n is equal to numbers from 1, 2, 3, and so on, up to n. Now what if we multiply the sequence by 5 times 1, 5 times 2, 5 times 3, 5 times 4, and so on? We must be able to get the sequence -5, 10, -15, 20, and so on. Then we can use the general rule to this sequence as 5 times n times -1 raised to n, where n represents numbers from 1 to n. We can just replace n with I, so that our sigma notation would be the summation of 5i times -1 raised to I, as I goes from 1 to n. This time, let us discuss the properties of sigma notation, as described by these formulas. The first property tells us that, in sigma notation, if the summation term is multiplied by a constant number, such as c, then it can be factored out. Say for example, if we have the summation of 3i, as I goes from 1 to 5, we can factor out 3, and multiply it by the summation of I, as I goes from 1 to 5. The summation of 3i on the left, when I is equal to values from 1 to 5, can be expanded as 3 plus 6 plus 9 plus 12 plus 15, which is equal to 45. Meanwhile, 3 times the summation of I, when I is substituted by values from 1 to 5, can be expanded as 3 times 1 plus 2 plus 3 plus 4 plus 5, which when simplified, is also equal to 45. For the second property, a sigma notation can be divided into distinct terms, each of which will retain the same sigma notation, if there are addition and/or subtraction operations between the terms. Say for example, if we have summation of 3i plus 7i, as I goes from 1 to 5, then we can express it as the summation of 3i, as I goes from 1 to 5, plus the summation of 7i, as I goes from 1 to 5. If we are to expand the left side of the equation by substituting I with values from 1 to 5, we will have 3 plus 7 plus 6 plus 14 plus 9 plus 21 plus 12 plus 28 plus 15 plus 35 equals 150. On the other hand, if we are to expand the right side of the equation by substituting I with values from 1 to 5, we will have 3 plus 6 plus 9 plus 12 plus 15 plus 7 plus 14 plus 21 plus 28 plus 35 equals 150 as well. Note that, for these two formulas, we set the index of summation as x, which means that they can start at any value of I in the sequence. Meanwhile, the next 4 sigma notation formulas are also very useful, however, they are only applicable if the index of summation is set at 1. To continue with the third property, this formula states that the summation of a constant number, as it goes from 1 to n, can be solved by multiplying that constant number by n. So if we have the summation of 9, as I goes from 1 to 10, then we can just multiply 9 by n, or in this case, it's 9 times 10, which is 90. Next formula allows us to add all the numbers from 1 to n, without really adding them. Instead, we use this formula. Although we can easily add numbers from 1 to 10, just by manually adding them by counting, which is 55, but what if we are asked to do so with 1 to 100? Or 1 to 500? Or even 1 to 1000? That is when the formula would be very helpful. So if we are asked to find the summation of I, as I goes from 1 to 1000, we will just substitute n with 1000, so that we have 1000 times 1000 plus 1 all over 2 becomes 1000 times 1001, which is 1,001,000, divided by 2, would be 500,500. And that is a very big number to just add manually, if we will not use the formula. For formula number 5, we can also add numbers from 1 to n, even if they are squared. I know, the formula is quite long, and although we won't need to use the formula for this kind of given. Since for this kind of given, we can just substitute I, with values from 1 to 5, square them, and then add them to easily get 55. But what if we have this summation of I squared, as I goes from 1 to 20? Using the formula would be the easier option. We can just substitute n by 20, so that we have 20 times 20 plus 1 times 2 times 20 plus 1 all over 6 equals 20 times 21 times 41 all over 6 are 2870. Our last formula allows us to add all the numbers from 1 to n, when they are raised to the third power, are cubed. Instead of getting their cubes and adding them, we can use this formula. Say for example, we have the summation of I cubed, as I goes from 1 to 10. Using the formula, we substitute n with 10, so that we'll have 10 squared times 10 plus 1 squared all over 4. Simplifying this, we have 100 times 121 over 4, or 12,100, divided by 4, which is 3,025. For practice, try to simplify this summation notation. You can pause the video to try them your own, and just continue when you're about to check your answer. To easily solve this, we must apply the properties or formulas we learned from the previous discussion. In this given, we can divide this into distinct terms, each of which will retain the same sigma notation. That is from formula 2. Hence, we can write it as 2 times summation of I, as I goes from 1 to 100, minus the summation of 3, as I goes from 1 to 100. Notice that we applied formula 1 to the summation of 2I, as I approaches from 1 to 100, so 2 was factored out of the summation notation. Using formula 4, we can evaluate the summation of I, as I goes from 1 to 100, using the formula. While the summation of a constant 3 can be easily simplified by 3n, according to formula 3. Now substituting n with 100, we have cancelling 2, so that we have 10,100 minus 300 equals 9,800. For the last given, we have to evaluate the summation of x times 2x plus 3x squared, as x approaches from 1 to 10. To easily solve this, we must distribute x first to the terms in the parenthesis, so that we have x times 2x is 2x squared, and x times 3x squared is 3x cubed. Now that we have the summation of two distinct terms, we can apply the second formula. We can also apply the first formula to factor out the coefficients of both x squared and x cubed. Hence, we can write it as 2 times summation of x squared, as x goes from 1 to 10, plus 3 times summation of x cubed, as x goes from 1 to 10. Next, we will use formula 5 for the summation of x squared, and formula 6 for the summation of x cubed. Substitute n with 10, we have simplifying 2 and 6, we have evaluating this, we have 770 plus 9075 equals 9845. Thank you again for watching. Hope you learned something from this video. If you do, kindly give us a like, subscribe, and hit the notification bell to get more lessons in mathematics for senior high.